In this lesson, we're solving polynomial equations. The problem with the equations that we're going to be solving today is, unlike yesterday's lesson where we were able to solve by factoring, today we're going to be solving cubic and quartic degree polynomials that, for the most part, are not going to be able to be factored. And so when factoring is not a possibility, we're going to learn this alternative method that will help us determine what the solutions to these polynomial equations are. So you're going to see a word that really is used synonymously with solutions, or we've used the word zeros in the past, but that word root there is another way of saying what are the solutions, or the zeros. And I'm going to show you in this lesson something that is known as the rational root theorem. That basically gives us a list of possible rational number roots. Remember what rational numbers are. They are the numbers like you would typically see, 1, 2, 3, the opposites of those. But the rational numbers also include fractions. That's what the word ratio refers to, fractions. So just think about all of our normal numbers plus the fractions, including the negatives. Okay? So this rational root theorem is going to give us a list of possibilities that we can use to check, and then I'll show you what to do once we've identified one of our rational roots. All right, so that's our goal for this lesson, is to solve polynomial equations that cannot be factored using this alternative method. So here's the way the rational root theorem, or I've called it here the rational root test. Here's how it works. To get the possible rational roots, the rational root theorem basically says this. If you make a list of all of the factors of the constant, that's the last number in our polynomial, and here they are, all of the factors of 8 in this case, both the positive and the negative, over the factors of the very first number, which in this case is 1. Well, the factors of 1 are pretty easy. That's just positive 1 and negative 1. Okay? So that fraction represents all of the possible rational roots. And since it's basically over 1, we can think of all of our possible rational roots as being these 8 numbers. Positive and negative of 1, 2, 4, and 8. So what do we do with those possible rational zeros? Well, we're going to make a table. And I'm going to make a list of those possible rational zeros that we got from the rational root theorem. Notice how they're listed down the side of my table. And then across the top of the table, I want you to think about what we did with synthetic division, where we use the coefficients and the constant. And that's what I have here. I have the coefficients and then the constant. Okay, so this table is really going to utilize synthetic division. It looks a little different than what we looked at the other day, but the concept is really the same. So to begin with this synthetic division process, I'm going to begin by bringing down this first number 1. And then you always multiply. Think of this number, in synthetic division we would have said that this number is in the house. So multiply 1 times 1, that is 1. And then you add that product to the next number. So I'm going to do the product of 1 and 1 plus negative 4, and that's negative 3. Okay, now the process repeats. Negative 3 times 1 is negative 3, and negative 3 plus negative 2 is negative 5. Okay, negative 5 times 1 is negative 5, and negative 5 plus 8 is positive 3. The purpose of this table is to determine which of these possible rational roots would give me a 0 remainder. Remember, if a number gives us a 0 remainder, it's called a factor. Well, obviously 1 is not one of my roots, so I'm going to keep looking. I'm going to test negative 1. So I'll bring down this first number, multiply -1 plus -4 is -5. Multiply -5 times -1, +5, plus -2 is 3. Now at this point, if you can see ahead of time that you're not going to get 0 as a remainder, then you can just go on to the next number. I know that's not going to work, so I'm going to test +2. Bring down this first one, multiply 1 times 2 is 2, plus -4, that's -2. Multiply -2 times 2 is -4, plus -2 is -6. Multiply again, and I'm not going to go any further because I can tell when I multiply and add 8, I'm not going to get 0. Well, this is the process. Now I've circled the number because I already know that the number 4 is a rational 0. So let's skip -2. Now you wouldn't necessarily know that yet, but let's just test 4 so that we can see what it looks like when we do find the actual rational root. Okay, so 1 times 4 is 4. 4 plus -4 is 0. 0 times 4 is 0. 0 plus -2 is -2. -2 times 4 is -8. -8 plus 8 is 0. So we have found our first solution. Remember, it's cubic, so I'm really looking for 3 solutions. One of them is a rational number. It's the number 4. The other 2 will be found by taking these numbers and making an equation out of these numbers. Remember what these numbers represent when we were doing synthetic division. This was our remainder. The -2 represents a constant. The 0 represents a linear coefficient, and the 1 represents a quadratic coefficient. So if you take those numbers and make an equation out of them, the equation looks like this. And when we solve this equation for x, we will find our other 2 roots, or solutions. So x squared equals +2, and then the square root of both sides, we get plus minus the square root of 2. So since this is plus and minus, that really represents 2 solutions to go along with the 4 that we found initially that gave us a 0 remainder. So all 3 of these are the solutions to this polynomial equation. Okay, let's try another one. I went ahead and listed all of the possible rational roots, all the factors of -8. It's just like we had before with +8. And then that would go over all of the factors of +1, but that doesn't change anything since we're dividing by 1. So I'll just leave it as these 8 numbers. Okay, synthetic division begins. Bring down the 1. 1 times 1 is 1, plus -2 is -1. Multiply -1 times 1, -1, plus 4 is 3. I can tell right away that I'm not going to get 0, so I'm just going to keep looking. For sake of time, let's test 2. Bring down the 1, multiply 2 times plus -2 is 0. 0 times 2, 0, plus 4. 4 times 2, 8. 8 plus -8, 0. So one of my solutions, or roots, is the number 2. The other 2 solutions, to make up the total of 3, will come from these numbers made up as an equation. Just like you learned with synthetic division. Remainder, constant, linear coefficient, quadratic coefficient. Solve this equation for x, and you will find your other 2 solutions. Now I want to show you something about those first 2 problems that is always true, and if you pick up on this pattern, then it will save you a lot of time in working your way through the table and trying to find the actual rational root. Do you notice these coefficients? 1, -4, -2. If you multiply 1, -4 times -2, you get +8. Okay? Notice on this problem, the coefficients 1 times -2 times +4, you multiply those three coefficients together, you get -8. So when that pattern exists, where the coefficients multiply together to equal the constant, do you see what the rational zero is? In this case, it's +2, which just happens to be the opposite of the number in front of x squared. Okay? Over here, going back to our first example, the rational zero is +4, which just happens to be the opposite of the number in front of x squared. So that pattern always holds true. Now, the pattern doesn't exist every time, but it's something that you should always look for, because that can save you a lot of time in hunting your rational zero. I still want you to list all the possibilities, because I want you to be familiar with this rational root theorem. So if this were the case, I do want you to list them all, but if the pattern holds true, you really only need to use synthetic division with the number that you know based on the results of pattern that we've concluded. You really only need to use the number 2 in this case in synthetic division, so that would save you a lot of time. So be on the lookout for the pattern. Well, in this case, unfortunately, the pattern doesn't hold true. 1 times 1 times -1 does not equal +2. So we're going to have to make a list of all the possible rational roots, which would be the factors of 2, plus and minus 1, plus minus 2, divided by the factors of 1, which leaves still the factors of 2. And then you notice I went ahead and listed our coefficients and constant across the top of the table, and we worked through the list. Well, there's only 4 numbers, so that's not too bad. So let's just show you one that doesn't work, and then we'll jump down to the one that does, just so you can get an idea of how this synthetic division process works. Alright, so bring down the first number, multiply. 1 times 1 is 1, plus 1 is 2. 2 times 1 is 2, plus -1 is 1. 1 times 1 is 1, plus 2 is 3. So obviously that is not one of my rational zeros. So let's just jump down to -2. I brought down the first number, multiply. -2 plus 1 is -1. Multiply, that's +2 plus -1 is 1. Multiply again, 1 times -2 is -2, plus +2 is 0. So -2 is one of my 3 solutions, or zeros, or roots. Okay, I'm going to use these numbers now in an equation to help me find the other 2 solutions. So my other 2 solutions will come from solving this quadratic equation. So notice where the numbers came from. Quadratic coefficient, linear coefficient, and constant. Okay, well, since this doesn't factor, and most people don't like to use completing the square, I'm going to solve this by doing the quadratic formula. The opposite of b plus minus the square root of b squared minus 4 times 1 times 1 all over 2 times 1. And simplifying the radical using the number I have my 2 solutions because it's plus minus. So we have a rational number, -2, to go along with these 2 complex numbers using the number I. Total of 3 solutions, but one of them is real. 2 of them are complex. Okay, so that's pretty much the process. There's that same answer. Here's your assignment. You're basically going to do this same process for all of the problems with the exception of 2 problems. On page 337, now it's okay if you use the table for these two problems, 13 and 14, but I would suggest that you really save this process that we're doing, this rational root theorem and synthetic division, save that for problems when you're solving equations that cannot be factored. Well, on page 337, numbers 13 and 14 can be factored. And we just looked at, in the previous section, in section 6.4, we learned how to solve those types of quartic trinomials that can be factored. So I would recommend that you fall back on what you learned in section 6.4 to solve these two. Everything else, regardless of what the directions tell you, you're basically using this same process. All the problems are pretty much done the same way, except for these two. And these two I would solve by factoring. Okay, I hope that helps, but let me know if you have any questions, and we'll check these out tomorrow.